Greetings, everyone, and thanks so much for joining us for this Smithsonian online conference. Today, we're going to be talking about understanding astrophotography, and this is a great way to think about where science and art meet. I think whether you come at this from a scientific curiosity standpoint, or you have artistic inclinations, or you really love the way the two come together, this is going to be an amazing session for all of us today. We're joining you from the Harvard Smithsonian Center for Astrophysics here in Cambridge, Massachusetts. And the pictures that you've been seeing on your screen are pictures that were taken right here. You're going to learn about some of the very processes and places and things that you're seeing in those photos throughout our session today. I'm going to go ahead, though, before we get started and just cover a couple of logistical things so that you feel most comfortable with participating in the session, because after all, we do these sessions live so that you can interact with us. So let me just go over a few ways that you can do that. First of all, on the left side of the screen, as many of you have discovered, there is a chat box, and we encourage you at any time to not only share questions you might have for our facilitators today, but also comments and reflections and takeaways, things you're learning, aha moments, and certainly even questions for fellow participants whose comments you might see. So please do jump in and share with us as we go along. We'll do our best to integrate as many of your questions throughout the presentation. We just asked, but I'd love to get a kind of updated response to this question. We know many of you participate in groups, but there are also people participating on their own. For those of you who are on your own today, you're not alone. You're with all of us and with people around the world who are, like you, very interested in this topic. So do take a moment, give us a sense as to how many people are gathered with you at your location. We have 6 sitting here at the table that I'm at here at the SAO today. Okay, excellent. Well, thank you for doing that. I also wanted to point out that if you need any help, you can write to smithsonian@learningtimes.com at any time for any technical assistance, so feel free to use that and take note of that address. You'll also note that we have closed captioning appearing at the bottom of your screen. Our colleagues at WGBH are listening to every word and doing their best to capture it for those of you who will benefit from seeing the captioning on your screen. If any reason you wish to turn it off, you can change the pull-down menu on the right side of your screen from WGBH to No Captions, and that will hide the real-time captioning. You can turn it on again at any point. I'd like to go ahead now and introduce Ashley Naranjo from the Smithsonian Center for Learning and Digital Access, who's going to give us an overview of the conference in context and some great follow-on activities so that you can dig even deeper. Ashley.
Thanks so much, Jonathan. So let's take a look. We have the Smithsonian Quest. So smithsonianquest.org is a site where you can find out all of the different badge opportunities that we have made available for students. We have a variety of water, land, civil rights, immigration, election badges, and museum object badges. And we're really thrilled to introduce our new digital badge. This badge is called the Astrophotographer. And with the Astrophotographer, Mary will give you a little bit more information in just a second, but basically students are able to control telescopes online through the MicroObservatory network, capture images, enhance the color and light just as Joe does in his everyday work, and compare images with professional images. And so here's just a few of the others in the series. You'll notice the environmental science ones are on this page. And then we also have some more historical and social studies type badges. Students can submit their responses to our activity prompts, make content connections with their everyday lives, and these submissions are actually ones that will receive feedback from Smithsonian educators like myself. I also wanted to bring your attention that this online conference session is actually one of a larger conference series. This summer we'll be highlighting the Smithsonian Astrophysical Observatory along with a Smithsonian affiliate, the Miami Science Museum, and the Space Telescope Science Institute. And so the dates for those sessions are available on the screen, Wednesday, July 10th, 2013 from 4 to 4:50, as well as Wednesday, August 14th from 4 to 4:50. So be sure to check those out as well. We also have an archive available of all our past online sessions. So if you missed part of this session and want to go back and share it with your class, feel free to visit our archive.
Thanks, Ashley. I hope you do and will check out those resources and really become an astrophotographer yourself. You're going to learn how to do that before the session is out today. You'll have some great next steps. I want to go ahead now and turn the floor over to Mary Dussault, who is the Instructional Systems Specialist at the Smithsonian Astrophysical Observatory. A little bit later, she's going to show us how to actually use a MicroObservatory telescope, but first she's going to set the stage for us, and I'm going to turn it over to Mary. Mary, thanks for hosting us today.
Well, you're very welcome. It's so exciting to join this conference and to be able to share some of the exciting science and science education resources that we have here at the Astrophysical Observatory. I just wanted to let folks know, if you may not be familiar with the Smithsonian Astrophysical Observatory, that unlike many of the Smithsonian units, we're up in Cambridge, Massachusetts, affiliated with Harvard, and we're jointly called the Harvard-Smithsonian Center for Astrophysics. And it's one of the largest centers for astrophysical research in the world, and astronomers here use telescopes on the ground and in space. There's engineers who develop some of the instruments for those telescopes, and folks study the sun in our solar system, solar systems beyond our own, and galaxies beyond our own. And today, you're going to hear from Joe DePasquale, who is the science imager for the Chandra telescope in the upper left here. At the observatory, we also try to share and unlock mysteries of the universe, not only for scientists, but for students, teachers, and the public. And we have a lot of education efforts going on, from the education and outreach efforts of science missions like Chandra and its incredible web pages and educational resources, to education research that we do for teachers, to innovative tools like the MicroObservatory online telescopes. And later on, after Joe tells you what he does, I'll show you how you can do something similar to what he does. So I just wanted to set that stage for folks. And Joe, it's all yours.
Okay. Thank you, Mary, for that introduction, and thank you, everyone, for joining us today. As Mary said, I'm the science imager for the Chandra X-ray telescope. So what that means is that I image science. Now, what that really means is that I get the opportunity to take data from the Chandra X-ray telescope and combine it with data from other telescopes to make our press release images. And I'll talk a little bit about how I actually go about doing that. But before I get into that, I just wanted to introduce you to Chandra telescope. As you see in this image here, this is the Chandra telescope. It was launched in 1999, and it was approved for a 20-year mission. It explores very hot regions of the universe, such as exploded stars, clusters of galaxies, matter around black holes. And the reason we have a Chandra X-ray Observatory in space is because Earth's atmosphere is opaque to X-rays. So X-rays are actually completely blocked if you were trying to observe them from the surface of the Earth. Chandra orbits the Earth in a highly elliptical orbit that goes a third of the way to the moon and back every 2 days. The data flow for Chandra is similar to what I've shown here in this little infographic. We take images of space in X-rays. They are collected by the detectors on Chandra, and then Chandra sends that data down to Earth through the NASA's Deep Space Network. Eventually it makes its way to JPL in California, and then it's shipped off to Cambridge, to the data center here, and then sent from one side of Cambridge to the other to get to SAO, where the data archive is kept and where I get to make the images out of it. So one interesting thing about X-rays is that to focus them is it's a very different process than what we do with optical astronomy. In optical astronomy, you're probably familiar with the telescope has a mirror at the bottom, and X-rays are actually optical photons are bounced off of that mirror. In X-ray light, the X-ray photons are actually so highly energetic that they would pierce through any mirror that tries to reflect them. And so the way we focus X-rays is using a what's called a grazing incidence mirror. It's essentially like skipping a stone off of a pond. where essentially we're just trying to guide the X-ray photons down through a focal plane using these grazing incidence mirrors. You may not be familiar with this, but Chandra is actually part of NASA's Great Observatories program. And this was a program designed to sample the universe in as many wavelengths as possible, from the shortest to the longest wavelengths, from the lowest energy to the highest energy wavelengths. Compton Gamma Ray Observatory is one of those. Chandra, of course, in X-ray, the Hubble Space Telescope in optical light, and the Spitzer Space Telescope, which is observing in infrared light. And so you might be wondering why we have all of these different observatories dedicated to doing the same thing, or looking at the sky. Why do we want to do that? Well, imagine for a second that you could only hear 3 or 4 notes out of the entire audio spectrum that people can hear with their ears. And you were listening to a piece of music with these fictional ears. It would probably sound very strange to you. You would hear 1 or 2 notes coming in and out, and otherwise it would be silent. But if you could expand your hearing and open up the full spectrum of audio, then you would get a much different picture of what's going on in your head. Well, this is exactly why we look at the universe in multiple wavelengths. It's because we want to understand physical processes on deeper levels. And you'll see when I show some images later on, when comparing different wavelengths of light, you get a very different view of what's going on in these objects. So this is the electromagnetic spectrum. This is what I've been talking about. The visible light portion at the top is what we see with our eyes. As you can see, it's only a very small portion of the entire electromagnetic spectrum, which ranges from radio waves in the longest wavelengths all the way up to gamma rays in the shortest wavelengths, and also highest energy. So long wavelength corresponds to low energy, and high wavelength corresponds to high energy and high temperature. And throughout my the rest of the talk here, whenever I show an image of space, I'll be showing this a little electromagnetic spectrum guide on the left side of the slide, which will indicate which wavelengths of light you're seeing in the image and then how they're color-coded. So keep an eye out for that. So why is it that we see visible light the way that we do? It turns out it's a biological thing. Our eyes just happen to evolve on a planet where it's orbiting a star that emits most of its light in this visible portion of the spectrum. So this curve on the right that you're looking at, let's see if I can get a pointer here. Okay, so this curve here, this shows you the light output of the sun, ranging from short wavelength to long wavelength from left to right. And so you're seeing where the sun peaks in its wavelengths is actually the visible portion of the spectrum. It's also putting out a lot of infrared light, which we perceive as heat. But again, the most of the light coming out of the sun is coming from the visible portion of the spectrum. So that's why our eyes see that light. You know, we've evolved on a planet where our eyes can see that. And that corresponds to red, green, and blue. And as it turns out, we can actually reproduce any image, or any color image, using those 3 colors, red, green, and blue, because they sample most of the visible light that we see with our eyes very well. Okay, so this is an image of a flower, obviously. I took this image with my cell phone, and the reason I included it here is because it's a great example of what red, green, and blue can give you in an image. This is actually an image that's composed of 3 different channels of red, green, and blue. And now, the computer doesn't care that those channels are red, green, and blue. They're really just grayscale images that are then colored red, green, and blue and co-added together accordingly. But there's no reason that we can't take those colors and swap them around and say change red to blue, or green to blue, and red to green. In doing this, we're still creating true color images that combine all the data that we saw in that original image. It's just shifted around a little bit. Okay, so now I'm going to shift focus a little bit. Before I get into X-ray astronomy, I just wanted to share with you my very first astrophoto. This is the core of the Orion Nebula, and if you're not familiar with a nebula, that's just a cloud of gas and dust where stars are actively forming in the case of the Orion Nebula. This was the very first image that I ever took. It was taken about 15 years ago in my college observatory. And I had really no idea what I was doing, but I managed to pull down this image. And it wasn't until I brought it out for this presentation that I realized what part of the Orion Nebula I was looking at. So moving on to the next slide, it's that very bright portion in the center of this image here, right there. That was what I imaged in my previous slide. So now what you're looking at here is the same region of the sky. It's slightly larger field of view. And this is an image of the Orion Nebula that I took with the MicroObservatory, which was processed with a program called PixInsight, and then also Photoshop to sort of enhance some of the details in the image. But this just gives you an idea of what is possible with the MicroObservatory.
Real quick question.
Sure.
Which came first, your interest in astronomy or interest in photography?
I would have to say my interest in astronomy came first. And then it was around high school where an uncle of mine gave me a SLR camera, and I got really interested in photography. And it wasn't really until I started doing this job, the Science Imager job for Chandra, that I combined my interest in photography and astronomy together.
Amazing. Thank you, Joe.
Sure. So moving on to X-ray light. This is the very first image taken by Chandra. This is the this is Cassiopeia A. It's a supernova remnant about 11,000 light years away in the constellation of Cassiopeia. This was, again, Chandra's first image, and it was the first time that if you look in the center of the image, there's a little bright dot, and this was it had been theorized to exist before, but this was the first time that it had been actually imaged. And so the very first image that Chandra ever took was a discovery. And that's because of the high angular resolution of Chandra, which means it can resolve very small details in objects that are very far away. This image is made up of 1 hour's worth of data. And also, just to give you a sense of scale, the diameter of Cas-A is about 10 light years, and the distance from our sun to its closest star is about 4.3 light years. So that just gives you an idea of just how large this object really is in space. Now, as I said before, this was an observation taken with 1 hour's worth of data. And now this is what we can get if we take more data. This is actually almost 12 days worth of observation time on this same object. And because we have so much more data, we're actually able to split it up into low, medium, and high energy X-rays and then make a true color image out of that. And you can see that reflected in our little electromagnetic spectrum guide on the left side there. Whereas before it was showing you one little marker, now there's 3 markers showing you red, green, and blue. And they are, just like our image of the flower, we've made 3 images in red, green, and blue and combined them together to make a true color image in X-rays. Now, one of the best parts of my job is to be able to take that data and combine it with data from other telescopes, like the Hubble Space Telescope, for instance. And that's what we're looking at in this slide. This shows you optical light in yellow taken by Hubble. And if I advance to the next slide, you'll get a good sense of why it's so important to look at the universe in many different wavelengths. Now that I've taken the X-rays away, you can see that this looks drastically different in optical light. And that's because the physical processes that occurred when the star exploded, in this case, it ejected gas into space, and that gas is colliding with interstellar material around it. It's not really excited in optical wavelengths, but in X-rays it's very energetic, so it's releasing a lot of X-ray light, but you can't see that in optical light. This is another one of Chandra's first observations. This is the Crab Nebula. This is actually a very zoomed-in view of the center of the nebula, where we're looking at a neutron star pulsar that is surrounded by a disk of material and is actually emitting jets on both sides of it. Excuse me. Now this is what happens if we get more data. This is, again, about 12 days worth of data of the Crab Nebula, and you get much more detail in the faint structure of the object overall. And now moving into the multiple wavelengths, this is what the Crab Nebula looks like in optical light. This is a Hubble Space Telescope image, true color, again, red, green, and blue. And this shows you the overall wider field view of the Crab Nebula. And again, this is another supernova remnant where all of the material of that star was ejected outward and is being shocked and interacting with the jets from the pulsar. And so you're seeing all this filamentary structure. It's really just a striking image. And it becomes even more striking as we add different wavelengths to it. This is the multi-wavelength view of the Crab Nebula, which incorporates the Chandra X-rays in the center. We've also added in Spitzer infrared data in purple, And then again, the optical data is now red and orange in this image. And so I'll just quickly cycle through each individual wavelength. Here's the X-rays. This is infrared. Infrared is tracing warm dust. So dust that was kicked out in that explosion, which is now being excited by interactions with that jet, is actually glowing, and that's what Spitzer is looking at. And then here's the optical view.
By the way, Joe, I think you're getting some great feedback, including from the students at Cayush Elementary in British Columbia, who are really appreciating seeing how you've set up the color and the spectrum legend on the left side of the slides. Very helpful.
Good. I'm glad to hear that it's well received. I know it's helpful to have a guide looking through these images. You really have no idea what's there if you don't have something to reference to. Okay, so now I'm going to jump a little bit into how I actually put these images together. And the image that we're looking at right here is the Andromeda Galaxy's multi-wavelength image combining Chandra X-ray in blue, Hubble optical in yellow, and Spitzer infrared in red. And we call this our Great Observatories image because these are 3 of the great observatories. These are interacting galaxies, in case you're interested. They're 2 galaxies that are actually colliding, and in the process they're kicking up a bunch of dust and generating huge clouds of X-ray gas, generating regions of star formation that are these bright white points in the X-ray image, and we'll talk a little bit more about that in a minute. So this is what the raw data looks like from Chandra. What you're seeing here are the actual detector, the CCD detectors, and in this one in the middle here, this is the actual source. That's what we were looking at before. That's the Andromeda Galaxies in X-ray light as a raw image. The raw data comes down from Chandra in a FITS format. FITS is Flexible Image Transport System, and Mary will be talking a little bit more about that soon because that is the same data format that is used by the MicroObservatory. So dynamic range is a very important topic when it comes to astrophotography. And what I mean by dynamic range is the range of intensity of light from the darkest to the brightest parts in your image. It turns out in astronomy, objects are very faint, but there's a huge range of light intensity. And that dynamic range is actually far beyond what you can see with your eyes or even what can be displayed on a computer. And so we do something called stretching or image scaling to show what's actually in the data. We use a scale function to manipulate the pixels in the image and before they're projected on screen. And so what happens is if you have, say, a linear projection, then you're seeing exactly the raw data as they appear on the detector. But if you scale that to, say, log scaling, which then compresses the brightest portions of your image and brings up all of the faint details, then you can actually bring out a lot more structure and detail in your image without oversaturating the brightest parts of your image. And so for X-rays, I typically use a log scaling. In MicroObservatory, there's a software package called MicroObservatory Image where you can do this type of image scaling to your data. This is just an example of what the Orion Nebula looks like in its raw data form from the observatory. And this little tool here called Adjust Image on the right side is what you would use to do image scaling in MicroObservatory Image. And again, Mary will talk about that soon. Now, angular resolution, I mentioned before, Chandra has a very good angular resolution. It can resolve very small structures and objects that are very far away. It turns out Chandra's angular resolution, as good as it is about 10 times worse than Hubble's angular resolution, which is 5 hundredths of an arc second. An interesting little fact about the Hubble angular resolution is that if your eyes could see as good as Hubble's, then you could stand in New York City and be able to distinguish 2 fireflies 3 feet apart in San Francisco.
Wow.
Yeah, Hubble's got some really great eyes.
By the way, one of our students who's logged in was curious about the cost of a telescope like Hubble or like Chandra. Any sense of scale for the student on that?
Multi-billion-dollar instruments.
And like a lot of hardware, it's also the cost of operating it. It's not just the device itself.
Right. Although most of the cost goes into building the research and development and the building, and then the cost of maintaining it is actually much smaller.
Great.
Yeah. So the reason I bring up angular resolution here is because that becomes a very important part or component of combining images. I can't just take an image from each observatory and slap them on top of each other and hope that they work. I actually have to scale each image to the other one to make sure that all of the objects overlap each other in the proper coordinate locations on the sky. So typically I would use Hubble as my guide because it has the best angular resolution, and we don't want to lose that detail. Now I can compare. Spitzer's angular resolution is about 1. What I was showing here in these green boxes is just an example, 5 arc seconds per side, and an arc second is just a measurement of angular resolution. And in each of these images, that green box is the same exact size. So Spitzer's angular resolution of 1.2 arc seconds, that green box becomes very small because Spitzer cannot resolve the same amount of detail and structure as the other observatories. And then here's what the MicroObservatory angular resolution looks like. There is actually a green box in there. It is the size of a pixel in that image. The MicroObservatory's angular resolution is 5 arc seconds per pixel. Something else that I have to keep in mind when I'm putting together our press release imagery is composition. And as a photographer, that's something I'm always thinking about. When I take an image like this, for example, this is the Boston skyline. I like this image because I feel like it conveys pretty well the rule of thirds, which is sort of a guide to taking aesthetically pleasing images. I try to keep that in mind when I'm composing my astronomical images as well. Here's an example of an image that we did a few years ago of a star-forming region, a nearby star-forming region. And I think this image captures that rule of thirds ideal pretty well. There's some interesting structures on the left side and the bottom side, and they all sort of work together to draw your eye towards this central region where the purple X-rays are exciting and eroding the clouds of infrared gas that you can see in this image.
One of the interesting things your composition lesson here brings out, I think, is the idea that often we think with science that by the time we arrive at an answer, we've found something definitive, something quantitative, and yet you're applying and sometimes coming back to and reapplying techniques to bring out new information. In a lot of artists almost feel like their work is never done. They're always always putting more paint on. How do they know when they're finished? Do you know when you're finished with an astro photograph?
Actually, it's funny you said that because I'm also a musician, and right now my band is working on an album, and we never know when to stop. We're always adding tracks to it, and I feel like it's the same thing with the imagery. It's hard to know exactly when you're done. You can always go back and tweak something here or adjust something there. What really helps for me is to have a group of people in my team who I bounce these ideas off of and these images off of, and we sort of reach a group conclusion together as to when are we actually done with this image. What's the best look for it? So layering the images together, the way I do that is with Photoshop, and I know some of you here, at least half of you according to the poll, are Photoshop experts. So after I've done everything that I mentioned before, scaling and bringing the resolutions together for these images, I bring them into Photoshop and I bring them together. So here's our Antennae Galaxies image. This is just the optical. There's the infrared and the X-ray. And then for the final version of this image, what I was showing in the optical just now was actually a 3-color optical, red, green, and blue. And one of the things that I try to do with my imagery when we're doing multi-wavelength images is to avoid color confusion. And so in this image, if I change that red, green, and blue optical to just a single color, like yellow, this reduces the amount of color confusion that you can have when you look at this image. Looking at this, you can say definitively that anything that I look at that's red in this image is coming from infrared data from Spitzer, and anything that's blue is from Chandra, anything that's yellow is from Hubble. And it's not as easy to say that when it's a 3-color optical image combined with the other two.
Is it just me, or do you see a head or a face in that image? It might just be me. But do you sometimes see forms and shapes that remind you of other things in these images?
We definitely do see that, yeah. And it happens a lot, actually. In our team meetings, we go through the images that we're looking at for potential press releases, and oftentimes people will say, well, that looks like a cat, or there's a ball flying through space or something like that. It's very easy to find shapes in these that you can identify with. So what I wanted to do here is just briefly talk about exactly how we create the three-color image in just X-rays to make a true color or a natural color X-ray image. This is an image of a supernova remnant called E102. It's in the Small Magellanic Cloud, and this is a true color image where I've taken data and split it up into three different color bins. And the way that I do that is to actually look at the real data. This is the X-ray spectrum of E102, going from low to high energy on the bottom axis, and then intensity on the vertical axis. And so in this image, we're seeing actual elements that are emitting X-ray light. And it just happens that the lowest energy elements here are oxygen, and then neon is the next highest, and then magnesium here. And what you're seeing is that there are different elements that were ejected by the star when it exploded, and they are now being excited to emit X-ray light. And you're seeing that intensity signature in this plot. Now I can use this as a guide to creating my three-color image and say, I want to take three different bins of data. And I'm going to take the lowest energy where the oxygen is emitting and make that red, and then the other two regions, the neon, magnesium, and silicon and sulfur, and I want to change those to green and blue, respectively. And I go in and I do that, and I make an individual image in each one of those color bands. So now I have my red, green, and blue images, just like our flower, and I pull them together to create the final version of the true color X-ray image. And the thing that's really helpful by doing that is that I actually get more information out of this single image. Now that I've done that, I know that anything that I see in this image that's red is actually coming from oxygen emitting X-ray light, and so on with the other elements. Those colors actually mean something in this image. And of course, as I like to do, I also combine it with data from other telescopes, like the Hubble Space Telescope. And so this is our three-color optical image combined with three-color X-ray image. And this is one of those images where those colors actually work really well together and actually avoids the color confusion issue that I was talking about before. Here's another example of a supernova remnant observation. This is a press release we did just a few months ago. This is a more recent example and actually shows a little bit of how my own personal image processing techniques have evolved over time. You can actually see a lot more structural detail in this supernova remnant than in the previous image. And this is another great example of why it's so important to look in multiple wavelengths. If I take the X-rays out of this image, there's absolutely nothing there in the optical light. So let's look at just the X-ray image. And there that is. So again, this is another one of those images where the colors mean something. The blue in this image is corresponding to high energy X-rays and actually traces out the expansion of a blast wave from the explosion of the star. And then the red and green correspond to different elements that are emitting X-ray light within the star.
It's almost like you're an interpreter, a translator. As somebody might translate one language to another, you're helping us see and understand things that would otherwise be an empty patch of sky. It's pretty amazing.
Yeah, that's actually a great point, Jonathan. And one of the things that people who do what I do like to say is that instead of considering these images false color because it's not something we can see with our eyes, we actually like to refer to them as representational color images because we're taking information that we can't see and we're translating it into something we can see. And so it's a representation of reality, although it's not something we can actually see. This is an iconic image from the Hubble Space Telescope. This is the Pillars of Creation in the Eagle Nebula. And the reason I bring this up is because of this false color topic we were just discussing. This image is colored according to the red, green, and blue standard that I was talking about. But as it turns out, if you look at the actual filters that were used to make this image, they correspond to different colors than red, green, and blue. This is oxygen 3, H alpha, hydrogen alpha, and sulfur 2. And those are just different elements that are emitting light in optical wavelengths. But those elements emit light in very specific wavelengths that actually correspond to different colors than what they are in this image. So I went back to the Hubble archive and pulled out the original data set, and I've colored it according to where it actually falls. And what you get is an image that still shows you the same structure and the same information, but aesthetically it's not as pleasing. And I'd argue that you're not getting as much rich detail out of it as you do when you color it according to the true color red, green, and blue method. And so it's very important for us to remember that as astrophotographers, that there's a lot of information to pull out of these images in their color form. And so with that, I actually, I'm forgetting something. This is the scale of the image. I just wanted to again give you an idea of the immensity of these objects in space. This cloud on the left here is actually 7 light years tall. And remember what I said before, the distance from the sun to its nearest star is about 4.3 light years. And so what that means is, I don't know if we can even see this on the slide, but there's a little circle at the very top where that arrow is pointing. And that circle corresponds to the size, roughly, of our solar system. The sun and all the planets. They would fit within that circle. And so with that, I would like to thank you for joining me today, and open up for any more questions.
Thank you, Joe. You've clearly sparked some amazing levels of interest from people who are here. I'm just going to sneak in one question, then we'll see if we have some time at the end after Mary. It's to some extent brings us down to earth so that we can go and get a taste of, in a real way, what you do each day. A student at Ashcroft Elementary was curious. You mentioned a little bit earlier about how you got your first SLR camera, but did you go straight to astrophotography, or did you do basic photography first?
I did do basic photography first. I mean, I actually grew up in a time where you learned how to do photography in a dark room with real film, real cameras. And I used a lot of that information when I got my first digital camera. You have a better understanding of how the camera works and why it does what it does. So I definitely started with basic photography and worked my way up from there.
Excellent. I see another question that we're going to come back to. Actually, no, really fast. Tarla Ray asks, what's inside a black hole? This is a timely question.
Yes, it is a timely question. As it turns out, we have a press release for Chandra coming out today at 2 o'clock. So be sure to check out the Chandra website, chandra.harvard.edu. And the reason it's a timely question is because the press release is all about black holes. There's a group of researchers who have discovered a whole plethora of black holes in a nearby galaxy, the Andromeda Galaxy. And you can learn more about that on the press release. But as far as what's inside a black hole, if you can figure that out, then you are due for a prize.
All right, we'll
yes. Yeah, there should be a badge for that.
Exactly. We'll have a digital badge. Let's go ahead. We'll keep you on hand for more questions. And Mary Dussault, we're gonna head back to you for some ideas of what we could do with all this amazing information.
Yeah, great. I saw that many people on the conference wish they had your job, Joe, and we all do, because it's very cool. And to some degree, you have the opportunity to do just what Joe does, and that's what I'm going to tell you about now. Because one of the things we like to do in the science education department here at the Harvard-Smithsonian Center for Astrophysics is share the amazing science that gets done with the public. And one of the ways to share that is through opportunities to be the astronomer. And one of those opportunities is to actually control our MicroObservatory robot telescopes. Now, the scientists who use the Chandra X-ray telescope, they don't actually look through an eyepiece the way we used to study the sky. That data comes back in the form of digital data that you then process, and the telescope is controlled remotely. And we have 5 little telescopes. These are about 3 feet tall. You see 2 of them here. This is Ben and Cecilia. The 5 telescopes all have names. They're Annie, Ben, Cecilia, Donald, and Ed, and all named after famous astronomers, which I'll let you all figure out through some research. And these are 2 that are at the Smithsonian Observatory in Arizona. We also have 2 on the roof here in Cambridge, and you can control them yourself, and I want to tell you how to do that. The MicroObservatory telescopes are completely automated. There's no human in the loop, and we're going to show you a little movie as I talk right here. So if you go to the telescope control webpage, which I'll show you in a moment, when you send your instructions to the telescope that night, the telescopes, here's a movie of one of the telescopes moving on its own. Your instructions get sent to the telescope, and that night at sunset, the telescope starts taking all the images that were requested that day and sends them back in an email. So you're seeing, this is, I think it's Ben. Can't quite tell the nuances close enough to see whether it's Ben or Cecilia, but anyway, moving to look at objects in the sky. So, all right, how do you get to control those telescopes? You go to the next slide, microobservatory.org, and this landing page has several different portals to the telescope, and some of which have limited access, but the one that is unlimited access, anyone with an email address can control the telescope through the link that says MicroObservatory for Everyone, and it was funded by NASA, so it's called Observing with NASA portal to the telescopes. And when you click on that link, you get to our site for controlling the telescope. You'll see a number of ways to navigate through the site across the top, including tools and tutorials and ideas for projects to do with the telescope. But you want to click on Control Telescope, and you'll get to a first page that looks like the one on the left here. So essentially, we give you a menu of targets in the sky that you can take images of, and some of the targets that Joe just showed you from the Eagle Nebula, that famous iconic image from the Hubble telescope, is one of our targets, to the Crab Nebula. You can take many of those images at, admittedly, a much lower resolution. As you remember, a single pixel of the MicroObservatory has a lot of more detail at the Hubble image, but you can get some great images. So you choose your target, and then you'll get to a page that looks like the next page, which is really where you are sending specific instructions about how to take that target to the telescope. And the three parameters that you set for the telescope are field of view, exposure time, and filter. Now, the thing to realize is that you're actually controlling a real instrument when you click, when you click on these settings. Field of view, if you remember that photo of the telescope and the video I just showed you, there were two little openings in the front of the telescope, two apertures, and one of them is the finder camera, which has a very large field of view, so objects appear small in it because it has a large field of view. That's the 10-degree field of view. If you held your fist up at arm's length against the sky, that's the portion of the sky that you would get an image of. So some kind of spread out clusters of stars, we use that finder to look at. And the main aperture of the telescope, the main view, gives you a 1-degree field of view on the sky, and that's the portion of the sky if you stick your pinky out at arm's length and try to cover the moon, for example. You'll see that the moon fits well within your pinky, and you get a great image of the moon using the MicroObservatory telescopes. The second parameter that you want to set is exposure time, and Joe talked about, he showed you two images of the Crab Nebula, one of which had a much shorter exposure time, and then the other had a lot more, and you got a lot more information in it. So you control how long you want the shutter to stay open, and for dim objects, you need the shutter to stay open for a much longer time, whereas bright objects like the moon, you would want a very short exposure time. And when you set that setting, you are actually instructing this physical shutter in the telescope how long to stay open and to let light fall on the CCD detector that is inside the MicroObservatory telescope. So you set field of view, exposure time, and the third thing you get to set is actually whether the light goes through a filter or not. And this is the way that the the detector of MicroObservatory does not actually see in color. It only detects bright and dark, places where a lot of light falls and places where a little light falls. So you actually have to do exactly what's done with the Hubble Space Telescope, which is to use those filters. Joe mentioned there was a filter, hydrogen, what was it?
Alpha.
Hydrogen alpha filter in that Eagle Nebula, and then a sulfur?
Yeah.
And an oxygen filter,
Yeah.
right? Very specific. Well, we have red, green, and blue filters. So each of these filters will let through that color light, but not the other colors coming from the object. And you can determine that and use those filters to actually create a representational or true color image of the objects. There are only a few objects for which we have all filter selections, so you'll have to do a bit of experimenting, and nebulas are great objects to take 3-color images of. So, unlike Chandra, optical light won't go right through a mirror, so the MicroObservatory telescope is a regular reflecting telescope, and this image just shows you the optical path. Light from objects in the sky bounces off a 6-inch mirror at the back of the telescope, back to a little diagonal mirror, and then up the detector at the top of this little diagram here. Is where the detector is. And this pink circle represents the filter wheel. So these are all the physical things that you are actually setting as you use the website to get an image back. You'll also notice that the MicroObservatory telescope was not in a dome. It's built like a tank. It was custom made, and it ends up taking images rain or shine. So you may experience some of the frustrations of a real astronomer, as you may get back images that are either partly cloudy or completely cloudy, and you actually don't get anything back. But that's also why we have telescopes in Arizona. It's less frequently cloudy there. So the next day you'll get an email with a link to your image that looks something like this, and you'll remember Joe mentioning FITS images. Flexible image transport system. And so you'll want to use the FITS image to do your astrophotography. And we have we have an image processing software package. There will also be a link to that in the email you get back from the telescope. That is, Joe showed you a frame from it, and I'll show you that again as well. But it allows you to bring out details that are hidden in the raw image that comes back from the telescope. It allows you to do that image stretch that Joe talked about that he does, allows you to assign color tables. And this is a screenshot of that software. We do have a number of video tutorials that will walk you step by step through using the image processing software, through downloading it, using it, opening and processing an image. And I encourage you to use those step-by-step video tutorials rather than having me try and go through them here, because you can stop and start them and really see what you're doing as you use the image processing software.
And they're really fantastic. We're just showing you a quick example of one of them right now on the screen.
Great. I'm not seeing. Right, so this tutorial is showing you just how to click on your email and how to get to the software, download it, how to use those processing steps. This software also will walk you through each of these menus in your software about adjusting the image, using the color tables, using features to sharpen or reduce noise in your image. And those tutorials are on the webpage in the software. So these are some samples of the kinds of images that you can get and the kinds of enhancement that you can do. And really, you all need to try it yourself. I can't emphasize enough the astrophotography badge is a great opportunity to practice your skills and try it out and get some feedback about how you're doing. And really, you just want to do it yourself. There's video tutorials for also doing advanced image processing of combining red, green, and blue images in the same kinds of ways that Joe combines high, medium, and low energy X-ray images to create a representational image of those supernova remnants. You can do the same with something like at the Orion Nebula, as you see here.
Mary, quick question as we get towards the end. A quick thought here. Obviously, there are many reasons to go try this out for oneself. Curiosity, learning, trying it out. Have you found that people are contributing their images back? Have any people actually made discoveries online?
Yeah, as a matter of fact, while these are small telescopes, they're pretty powerful in terms of they have a huge dynamic range of the kinds of things you can do with them. We have an amateur astronomer who has been using the telescopes to look at supernova that have gone off in some of the galaxies that are part of the MicroObservatory targets, and has created light curves, and has actually written journal articles to the British Astronomical Society journal using MicroObservatory telescopes. So your range of things you can do, from simply taking an image of the moon to taking an image of all the phases of the moon and creating a calendar or an animation, to doing photometry and variable stars astrophotography, and even detecting planets around other stars. There's a great range of things you can do.
What's incredible about your topic, Mary and Joe, what you shared with us today, is that once it seems so far away, so out of touch, something that we can't really get immersed in and learn about firsthand, and yet you've shown us that even without having specialized skills to begin with, we can really jump in and be a part of the scientific discovery process and the creative aspects of what you do. And I think for a lot of people, you've really turned us on to a whole new world. I think if you haven't seen it, Joe also answered a question of one of the students in the chat today about how he made the transition into astrophotography, and it shows you that you can take different paths and start to combine different disciplines and different interests. And that was exactly one of the key topics we wanted to talk about today. We'll stay on for another moment or two to answer some questions, but I did want to just give folks who need to drop off right now a couple of quick next steps. First of all, we'd love to get your feedback about today's session. It's how we continue to bring you content of interest and people who can inspire us, and get your feedback about the format and otherwise. So click the evaluation link at the top left corner of your screen. We hope you can respond to the questions that are there now, but if you're in a group, please go ahead and leave it open on your screen for the side so you can respond to it after we've wrapped up today. But we really would appreciate your feedback. I'm also going to just move that evaluation link down just a touch to remind you that there's the Understanding Astrophotography badge. And for those of you who have participated today, you registered, we'll be sending out and signed in, we'll be sending out this badge, which says you've taken the first steps to learn about astrophotography and that you're on your way to actually experiencing and contributing to the field firsthand. And that's where the Smithsonian Quests come in. So we hope you'll take your first badge for being in this web conference and that make that the first step towards your ongoing exploration in Smithsonian Quests. Okay, let's go ahead and just take one or two more questions, if that sounds good. We're getting lots of applause and lots of woes and oohs and ahs from what we experienced here today. There's a question that advice for somebody who wants to become an astrophotographer as a career. What kind of advice do you have?
As a career, it's something that's hard to actually make your way into. I feel like I kind of stumbled into it, sort of roundabout way. I majored in astronomy and astrophysics in college, and I intended to go through and do like the research track and everything. But I sort of made my way into astrophotography. I'd say if you have a real interest in it, then definitely pursue all of the available resources out there online. There are user forums. I use this software package called PixInsight, which is almost like Photoshop for astrophotographers. It's totally geared towards astrophotography, and it has a very active and very vocal user community. And if it's something that you're really interested in, there's a trial version of it. You can use data from the MicroObservatory even to process with PixInsight, and you can go through the forums of PixInsight and learn so much valuable information. There are people who just have all of these free resources for learning how to do astrophotography.
It's an amazing world where we can tap into a community of people with a common interest. Mary, you had some thoughts on this too.
Well, I just encourage you. There may not be a huge worldwide call for astrophotographers, but there is opportunity for everyone to become an amateur astrophotographer.
Yes.
And so that is something everyone can do.
What would you say is one of the? It's a great point. As both of you think about your work in this field, and when you talk to people who are interested but aren't as involved in it as each of you are, when it comes to kind of understanding our role on this planet and what we're supposed to be doing here, any kind of quick philosophical takeaways that have changed the way you think about the world as a result of looking at other worlds?
Wow.
I know, a real little question to end on.
It just makes me think back to in college when I first looked at Saturn and I saw the rings of Saturn through a telescope. I mean, that's one of those things that's just a very inspiring moment to witness something that's so far away and so much bigger than everything that is the world that we are. At the same time, it makes you feel insignificant, but it also makes you feel there's a purpose here, that we are the universe trying to understand itself, essentially. And that, that's like from Carl Sagan, who said that we are star stuff. And so all the elements that make us up came from stars that exploded billions of years ago in supernova explosions. And so we really are the universe trying to understand itself.
Well, on that very meta, inward and outward looking note, we're going to thank everyone for being here and asking such great questions, and for appreciating the great work that both Mary and Joe do here at the Smithsonian Astrophysical Observatory. And we want to thank all of you, and we hope you'll join us for the upcoming sessions. We have another session on this topic, especially focused for educators and those who wish to learn even more deeply about how to use the MicroObservatory that Mary walked us through. That's coming up in August, and Ashley's going to put a link in the chat or some additional information. And we have other sessions coming up, as she mentioned, in August that turn our eyes back to outer space. So we hope you'll continue to be part of the Smithsonian Education Online Conference Series. Visit smithsonianquest.org so that you can continue to dig in deep and learn a lot about all sorts of topics, including the ones we covered today. So until next time, we'll see you all soon, and please join me in thanking Mary and Joe. Take care, everybody.